Okay, in this video we'll be going through the 2023 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself, once you completed the question or get stuck, unpause the video to see how I go about getting the answer. Kate is learning about capacitors. She investigates a capacitor found in a camera. The capacitor is labeled 185 nanofarads. The camera also contains a 1.5 volt AA battery. Show that the energy stored by the capacitor when it is fully charged by connecting it to the battery is 2.08 times 10 to the negative 7 joules. Alright, so we know our EP is equal to half QV. We are given the voltage across the capacitor because remember, when the capacitor is fully charged, the voltage across the capacitor is equal to the EMF of our battery, okay? However, what we don't know is the charge stored on the capacitor. But what we do know is that the charge stored on the capacitor is equal to the capacitance times the voltage. And so we can simply plug this into here and we get EP is equal to half CV squared. And so we are given the capacitance, and so we can simply plug it in, and we get half times our capacitance of 185 times 10 to the negative 9, alright? Times 10 to the negative 9 is how you convert from nanofarads, alright? And that's multiplied by 1.5 squared. And this gives an energy of 2.08 times 10 to the negative 7 joules. There we go. The diagram below shows a circuit used to charge the capacitor. The battery has an internal resistance of 0.27 ohms. Assume that the rest of the circuit has no resistance. Sketch a curve by plotting at least 4 points on the grid opposite to show how the charge on the capacitor varies with time, once the switch is closed. Your answer should indicate the time constant for charging the capacitor and the maximum charge that will be stored on the capacitor plates. Alright, so we usually don't plot a charge versus time graph, okay? So this might throw some people off, okay? Because you may not know the shape of this graph. However, if we remember what voltage is the potential difference across our capacitor plates, okay? So it's the difference in energy per coulomb of charge across our capacitor plates, alright? Alright, so when our voltage is max, that means we have the maximum amount of charge stored on our capacitor plates, okay? And so when our voltage is max, the charge on our capacitor is also max. And so therefore, the charge on our capacitor plates is directly proportional to the voltage, alright? And we also know that this relationship is true because we know that Q is equal to CV, okay? And so therefore, the shape of our charge versus time graph is going to be the exact same shape as our voltage versus time graph, which is going to look something like this, okay? And so therefore we can figure out our time constant because our time constant is equal to the resistance times the capacitance. The resistance is given up here as 0.27, and our capacitance is still 185 nanofarads. Alright, and this gives a time constant of 4.995 times 10 to the negative 8 seconds, okay? And I'm going to round this to 5 times 10 to the negative 8 seconds, okay? The reason for this is because our x-axis is in terms of times 10 to the negative 8, as you can see right here. And as you can see, our x-axis is split in fives very, very nicely, okay? And so that just makes it easier on ourselves, alright? So obviously, when the time is equal to 0, this is when we're going to have 0 charge on the capacitor plates because that's when our power supply is first turned on. So therefore, at 0 time, we're going to have 0 charge. So our first point is over there. And so to find our next point, that is after 1 time constant, so that's after 5 times 10 to the negative 8 seconds, we know that this value is going to be 63% of our maximum value. And so we can calculate that by first calculating our max value. And we know our max value is going to be Q is equal to CV, where our capacitance is still 185 times 10 to the negative 9, multiplied by the voltage of 1.5. And so this gives a maximum charge of 2.775 times 10 to the negative 7 coulombs, alright? However, as you can see, our x-axis is in terms of times 10 to the negative 8, and so therefore, to make this easier on ourselves, I'm going to convert this into times 10 to the negative 8 also, and this equals to 27.75 times 10 to the negative 8 coulombs, okay? And so therefore, our max charge is going to be somewhere over here, okay? And remember, our capacitor is considered to be fully charged after 1, 2, 3, 4, 5 time constants, okay? And so as you can see, this is when our charge is going to be max. So now to figure out the charge on our capacitor after 1 time constant, we can take our maximum charge and multiply it by 1 minus 0.37. Okay, so this is obviously equal to 0.63. Okay, and this equals to 17.48 times 10 to the negative 8 coulombs. And so that's roughly going to be right over here. Okay, after 2 time constants, we take our same max value and we multiply it by 1 minus 0.37 squared. And this equals to 23.95 times 10 to the negative 8 coulombs. Okay, so this is equal to roughly over here. After our 3rd time constant, minus 0.37 cubed. And this is equal to 26.34 times 10 to the negative 8 coulombs. And so this is roughly over here. And finally, our 4th time constant, 1 minus 0.37 to the power 4. This equals to 27.23 times 10 to the negative 8 coulombs, okay? And so that is roughly right over here. And so as you can see, we have a nice logarithmic graph like so. There we go. Although the capacitor plates are rolled up, they act like two middle rectangles measuring 3.2 times 10 to the negative 2 meters by 1.83 meters, with a dielectric material in between. If the dielectric material in the capacitor has a relative permittivity of 2.1, calculate the distance between the two middle rectangles. Alright, so we know the equation for our capacitance is epsilon naught, which is our permittivity of free space, times the relative permittivity, times our area, all over our distance. We are given our dimensions, and so we can find out our area. That's going to be equal to 3.2 times 10 to the negative 2, multiplied by 1.83, and this gives an area of 0.05856 meters squared. And so therefore, as we're trying to find our distance, and we have all our other values, we can now rearrange for our distance, and we get our distance is equal to epsilon naught times our area, all over our capacitance. And so now plugging in our numbers, we get 8.85 times 10 to the negative 12 times 2.1 times 0.05856 all over 185 times 10 to the negative 9. And this gives a distance of 5.88 times 10 to the negative 6 meters. There we go. The charged capacitor can be discharged through a lamp by pressing a switch. In the camera, the lamp flashes when a picture is taken. Kate fully charges the capacitor with a 1.5 volt battery, but then when the bulb is connected, it barely glows. Inside the camera, she finds wiring that allows the capacitor to be charged to 200 volts. Explain how this arrangement allows for a much more powerful flash. In your answer, you should show how the energy stored in a fully charged capacitor at 200 volts compared to 1.5 volts, how the higher voltage increases the initial current from the capacitor when it's connected to the bulb, and how the brightness of the flash will be affected by the higher voltage. Alright, so we know that the energy with 1.5 volts is equal to 2.08 times 10 to the negative 7 joules. Alright, we found that in our very first question, this question right here. And so the energy with 200 volts, okay, is given as EP is equal to half CV squared. Our capacitance has not changed, so that's still 185 times 10 to the negative 9, multiplied by our new voltage, which is 200 volts squared, and that is equal to 3.7 times 10 to the negative 3 joules. Alright, and so as you can see, if we were to compare these two energies, we can see that this energy is times 10 to the negative 7, and this energy is times 10 to the negative 3. So already we can see that with 200 volts, our energy in our capacitor is way higher. We can find out just how much higher it is if we were to take 3.7 times 10 to the negative 3 all over 2.08 times 10 to the negative 7, okay? And this gives 17,788. And so what this is essentially saying is that the energy stored in our capacitor with 200 volts is almost 18,000 times greater than with 1.5 volts, okay? So it's much, much, much greater, okay? And so therefore, as V is equal to IR, and therefore I is equal to V all over R, because our voltage is much greater from 1.5 to 200 volts, therefore our current increases by the exact same proportion, okay? And so because our current is going to increase as P is equal to I squared R, therefore the current going through the bulb will also increase. Therefore, as there's more current going through the bulb, the power that is consumed by the bulb is also going to increase, and so the bulb is going to glow brighter. And this can also be said as the energy that is used by the bulb per second is going to be greater, okay? And obviously, we know this because the bulb has more energy to use, okay? And so you can write that in. Kate's school has a demonstration transformer. She connects a 12,000 turn primary coil to the main power supply of 240 volt RMS. She connects an AC voltmeter to the blue coil. Calculate the RMS voltage she would measure from the 600 turn secondary coil. Alright, so there's meant to be a picture here, but as you have probably seen, this picture is blank, it's grayed out, so it's no longer useful to us, so I have no idea what they're talking about when they say blue coil, red coil, and picture alongside, so I'm in the same boat that you are. But there is enough information from here that we can still get the right answer, alright, even though we don't have the full context. So as we can see from this question, this is a question of stepping up or stepping down the voltage in a transformer, and so we know the equation for that is NP all over NS is equal to VP all over VS, okay, where P stands for primary and S stands for secondary. We're trying to find the voltage in the secondary coil, okay, because it says over here. And so therefore we can rearrange for the voltage in the secondary coil, and we get VP all over NP divided by NS. The voltage in our primary is 240 volts divided by the number of turns in the primary, which is 12,000 all over the number of turns in the secondary, which is 600, and this gives 12 volts for the voltage in the secondary coil. There we go. The two coils are held by a ring of laminated soft iron, which runs through the core of each coil. Explain why an AC voltage in the red coil produces an AC voltage in the blue coil, and the coils are wrapped around an iron ring. Alright, so the reason why the coils are wrapped around iron is because our iron core will increase the magnetic flux, and also this iron core / iron ring will direct the magnetic flux to the secondary coil, so it helps with that transfer process. So that's our second point. As for our first point, obviously as we're using an AC voltage, there's going to be an alternating current, obviously, because that's what AC stands for. And so therefore the current is constantly changing. And so because of this, there is going to be a constant change in flux in the primary coil. This change in flux interferes with the secondary coil, thus inducing an EMF within the secondary coil. And that's obviously due to Faraday's law, as Faraday's law is equal to change in flux over change in time. Okay, so if there is a rate of change of flux, which there's going to be an induced EMF, and obviously this EMF is going to be in opposite direction to the change that caused it due to Lenz's law. And so you can write that all in. Kate connects the 12,000 turn primary coil in a circuit with a 12 volt battery and a 12 volt car headlamp. Explain why the headlamp only comes on after a slight delay. Alright, so when we turn the car on, aka that's when the power supply is going to be turned on, the current is going to start to rise from 0, okay, because obviously when the car is off, the current is 0, and so therefore there's going to be a high rate of change of current. Therefore, due to this high rate of change of current, we know that the EMF induced in our inductor is equal to negative L change in current all over change in time, and so therefore if there's a high rate of change of current, the back EMF is also going to be high. How high specifically? This back EMF is going to be initially equal to the EMF of the battery, okay? Initially, it's going to be equal to the EMF of the battery. And so therefore, initially, we're going to have two opposing EMFs, which are equal to each other, and so therefore, initially, no current will flow throughout the circuit. However, over time, this rate of change of current will begin to decrease, and so therefore, our back EMF will begin to decrease up until the point that the back EMF is no longer present, and so at that point, our current is going to be a max, okay? And so therefore, our bulb will start to glow at that point, okay? And so you can write that in words. The power station that supplies Kate's area generates 50 kilowatts of power. The transmission line near Kate's house carries 50 kilowatts of power to an industrial user. The voltage across the transmission line is 220 kilovolts. The resistance of the transmission line is 4 ohms for every kilometer. Calculate the power loss as heat across a distance of 300 kilometers. Comment on whether the amount calculated is significant compared to a situation where the voltage is not stepped up to 220 kilovolts but is transmitted at 25 kilovolts. Alright, so we know that our P is equal to IV, okay? And so therefore we can calculate our current traveling through our transmission lines as our current is equal to the power divided by the voltage. The power is 50,000 watts all over our voltage, which is 220 kilovolt, which is 220,000 volts, okay? And this gives a current of 0.227 amps, alright? And so therefore to calculate the power loss, we can take P is equal to I squared R. Alright, and obviously we get this equation because we take V is equal to IR, and then we substitute the V into here, and then we get this equation right here. Alright, and so we get P is equal to I, which is 0.227 squared times our resistance of 4 ohms per kilometer. Okay, and so this is going to be the power loss per kilometer. So our power loss per kilometer is equal to 0.207 watts. Okay, and so our power loss for the entire 300 kilometers is 0.207 times 300, and this is equal to 61.98 watts, which we can round to 62 watts. And so right off the bat, you can already see that we lose 62 watts, but we're transmitting 50,000 watts. Okay, so you can already see that the power loss is very insignificant compared to the amount of power that we're transmitting. However, if we compare this to the amount of power loss that we would have if we were to transmit electricity with a voltage of 25 kilovolts, we would have our current is equal to our power all over our voltage. Our power is still going to be 50,000. However, our voltage is 25,000 volts, and this gives a current of 2 amps. Okay? Alright, so as we can see already, we are producing almost 10 times as much current. And so therefore we already intuitively know that current is what causes heat in our electrical components. And so we already know that this scenario is going to produce a lot more heat than the scenario right here, okay? However, we can figure out the exact numbers by using P is equal to I squared R once more. And we get 2 squared times 4, okay? So this is the power loss per kilometer, okay? So this is 2 squared, and that's equal to 16 watts. And so therefore, the power loss across the entire 300 kilometers is equal to 4,800 watts, okay? And so as you can see, 62 watts compared to 4,800 watts is a big difference. In fact, it is a difference of 300 times. So we lose 300 times more power in this method, alright? Okay, and remember, power is measured in watts, and watts is measured in joules per second, okay? And so we're losing 300 times more energy per second, which obviously is significant, and so you can write that in. Kate builds a circuit with a signal generator set to 200 Hz, an AC ammeter, and a lamp of 15 ohms, and a capacitor of 1.2 times 10 to the negative 6 farads. Show that the reactance of the capacitor is 663 ohms, and hence determine the impedance of the circuit. Alright, so we know that the reactance of our capacitor is equal to 1 all over omega c. We know our omega is equal to 2 pi f. Alright, we have our frequency of 200 Hz, and so therefore we have 2 pi times 200, and so this is equal to 400 pi. So now that we have all our numbers, we can plug them in. We have 1 all over 400 pi multiplied by 1.2 times 10 to the negative 6, and this gives a reactance of 663 ohms. Alright, and so therefore we can find our total impedance by using Z is equal to square root xc squared plus r squared. And obviously this equation comes from us doing vector addition of our phasor diagram, okay? And so this is equal to square root 663 squared plus our r squared, which is just the resistance of the lamp, because for all intents and purposes, a lamp acts pretty much the exact same as a resistor in terms of our calculations, okay? And so that's 15 squared. And this equals to 663.32 ohms. There we go. Kate increases the frequency of the signal generator to 200 Hz to 20 kHz and then to 200 kHz. Give an in-depth explanation of what Kate will observe in the circuit at each frequency compared to her observation in part A. In your answer, consider the effect of changing the frequency on the impedance of the circuit, the RMS current, and the brightness of the lamp. Alright, so we know that our reactance of our capacitor is equal to 1 all over omega c, and so therefore the reactance of our capacitor is inversely proportional to our angular frequency. We know our angular frequency is equal to 2 pi f, and so therefore our angular frequency is directly proportional to our frequency, and so therefore our reactance of our capacitor is inversely proportional to our frequency. And so therefore if we increase our frequency from 200 Hz to 20 kHz, alright, so we increase our frequency, therefore we're going to decrease the reactance of our capacitor. And so therefore, as our total impedance is equal to square root xc squared plus r squared, if we reduce the reactance of our capacitor, therefore the total impedance of our circuit is going to decrease. And as V is equal to IZ, if our total impedance decreases and our voltage remains the same, therefore our current is going to increase. And as the power through the lamp is equal to I squared R, if our current increases, therefore the power used by the lamp is also going to increase, and so therefore the lamp is going to glow brighter. And so that's what happened when we increase from 200 to 20 kHz. And so obviously if we increase from 20 kHz to 200 kHz, the exact same process is going to happen. We're going to increase our frequency once more. Therefore, the reactance of our capacitor is going to decrease once more. Therefore, our total impedance is going to decrease. Therefore, our current will increase, and therefore our power will also increase once more, making the lamp glow even brighter. And so you can write that in words. Kate adds a 0.2 Henry's inductor in series with the capacitor. While the signal generator is set to 2000 Hz, the lamp is off, but as she slowly decreases its frequency, the lamp suddenly glows brightly, but then goes off at lower frequencies. Calculate the frequency at which the bulb glows the brightest. Alright, again, because P is equal to I squared R, the bulb is going to glow the brightest when the current is the largest, okay? And we know that when we have an LCR circuit, which is what we have now because she added an inductor, the current is max when resonance occurs. Alright, and we know that the circuit is at resonance in an LCR circuit when the reactance of the inductor is equal to the reactance of the capacitor, okay? And the reason why the current is max when the reactance of the inductor and the reactance of the capacitor are equal is because they're 180 degrees out of phase, and so they cancel each other out, and so our total impedance is at a minimum, and so therefore our current is going to be our maximum, okay? And so therefore we can find this frequency if we take this equation, alright? We know that the reactance of our inductor is equal to omega L, and the reactance of our capacitor is 1 all over omega C, and so therefore omega squared LC is equal to 1. We know that omega squared is equal to 4 pi squared F squared, and so therefore 4 pi squared F squared LC is equal to 1, and so therefore F squared is equal to 1 all over 4 pi squared LC, and so therefore F is equal to 1 all over 2 pi square root LC. We know our capacitance, as that is equal to 1.2 times 10 to the negative 6 farads. Alright, that's given all the way up here, okay? And we are given our inductance of 0.2, and so we can simply plug in our numbers, 1 all over 2 pi square root 0.2 times 1.2 times 10 to the negative 6. Alright, and this gives a frequency of 324.87 Hz. There we go. Explain how the inductor affects the impedance of the circuit and why there is one frequency at which the impedance equals the resistance of the circuit, causing the lamp to glow the brightest. Alright, so this is what I went through very quickly before I solved this equation right here. We know that our XL is directly proportional to our frequency, okay, and we know that XC is inversely proportional to our frequency. Okay, and so therefore, if we increase our frequency, our reactance of our inductor is going to increase. However, if we increase our frequency, the reactance of our capacitor is going to decrease. Okay, and so we can see how they have sort of an opposite relationship, and we can see this in our phasor diagram where we have our XL coming over here, the resistance coming over here, and our XC coming down here. We can see how that they're 180 degrees out of phase with each other. However, theoretically, there is a frequency at which we can tune this circuit such that XL is equal to XC, alright? And when this happens, because our total impedance, okay, our total impedance Z, is the vector sum of R, XL, and XC, okay, and so this is just our vector addition, alright? Where we make a right angle triangle and then we do trig. And so as we can see here, XL and XC are 180 degrees out of phase, and so if they're equal to each other, because they are equal in magnitude but opposite in direction, they're going to perfectly cancel each other out. And so therefore, our phase diagram collapses into just our resistor value, okay? And because our total impedance is the vector sum of R, XL, and XC, if the values of XL and XC cancel each other out, so they collapse to 0, therefore, our total impedance is just the vector sum of our resistance, because these have cancelled each other out, okay? And so therefore, our total impedance is equal to our resistance. And obviously, we can see that this is when the total impedance is at a minimum value, because the reactances of the circuit don't add to our total impedance. And so because V is equal to IZ, if our impedance is at a minimum, therefore our current is going to be at a maximum because our voltage has remained the same. And so therefore, because P is equal to I squared R, if our current is at a max, therefore the power used by the bulb is going to be a max, and so it's going to glow the brightest. Also, another way in which you can explain how total impedance is the minimum, we know that our total impedance is equal to square root XL minus XC squared plus R squared, okay? And so if XL and XC are the same value, this term right here is going to collapse to 0, and so we get Z is equal to square root 0 squared plus R squared, which we know that's just equal to R squared, and square root R squared is just equal to R, and so therefore we get the exact same result that we had over here, okay? And so you can explain all that in words. And with that, we're done. See you.